We turn to derive some of the properties of an ideal gas from the partition function. So on the slide you see the partition function for an ideal gas, which is just the single particle partition function raised to the nth power and then corrected for overcounting by this factor 1 over n factorial. So taking the free energy is equal to minus k t log of z. We have a first term which is minus kt times n times the log of z1, and a second term which is kt log of n factorial. The plus sign here because we had a minus in front of the whole thing and we're taking the log of 1 over n factorial. Using Stirling's approximation for n factorial, or log of n factorial, we then arrive at this expression for the free energy on the bottom of the slide. Notice that if we expand this out, this quantity in parenthesis, the nkt over 2 pi h bar squared to the 3/2 is 1 over the quantum volume. This expression then just is the ratio of the volume to the quantum volume. The first part of the free energy becomes So when we come to take derivatives to derive the pressure, which we will do on the next slide, recalling that the pressure is given by minus the derivative of the Helmholtz free energy with respect to volume at constant temperature. This is made easy because there is only one term here that contains the volume, which is this. So d by dv of the log of v is just given by 1 over v. So, putting this back then into our expression for pressure, we end up with P is nkt over v, or if we choose 1 mole for which n is Na, so that nk is R for 1 mole, the gas constant, we have PV equals RT. You'll recognize this as the ideal gas law, here derived from the partition function of a microscopic picture of an ideal gas, but more readily in elementary classes derived from Boyle's law and Charles' law. So turning now to another thermodynamic property of the ideal gas, which is the entropy. So I've put up here again the expression for the Helmholtz free energy, and let us now take its derivative with respect to temperature to get the entropy. So S is minus dF dt at constant volume. Doing this is a little tedious, so I'm going to ask you to do exercise 324 and work through this. To do this, you'll need to remember the result I just gave you, which is that d by dx of log of x is 1 over x, and you'll make copious use of the result that the logarithm of a over b is log a minus log b. Once you've done this, you'll end up with the expression at the bottom of the page here that S is nk, the log of the ratio of the quantum concentration, so that's the quantum limit, divided by the actual concentration, plus this rather strange constant here, 5/2, which actually comes from counting up all the n log n terms properly. First of all, notice that the entropy scales with the number of particles. It's an extensive quantity, as it should be. This additive constant was really a triumph for Sacker and Tetrode, who derived this result, since it set the absolute scale of entropy. But we have in here the very important result that the entropy scales like the log of 1 over the actual concentration, or minus the log of concentration. Now, recall that the free energy has a term that's the internal energy minus T times S. So the contribution to the free energy then scales as minus times minus is a plus N K T log of C. So the higher the concentration of an ideal gas, the higher its free energy. And this has an important consequence for chemical reactions. So we just summarize the statement here that the entropy, free energy is increased by a term log C, the entropy decreased by a term minus log C. And so there is a thermodynamic driving force then changing the free energy of reactants and products in a chemical reaction, and where you, as you may have come across this result from the law of mass action in elementary chemical kinetics, you see here that it is a statistical result of the entropy as derived from the partition function. Let us illustrate it here with a simple chemical reaction. A plus B goes to C. Now, normally this will be measured in standard conditions, and the free energy difference driving this reaction is usually confined for 1 molar A, B, and C in standard temperature and pressures. And this is given the symbol delta G0. Now, of course, chemical reactions can be carried out at any concentration. So the question is, what is the actual delta G for a reaction given that the concentrations are not 1 molar? We can work this out using the result we just obtained for the correction to the free energy owing to the concentrations of reactants and products deviating from 1 molar. So in the case of the reactants, we know that there is a term plus RT log of A plus RT log of B. I've put these little square brackets around here to show that these are ratios of the concentration with respect to 1 molar. This ratio is called by chemists an activity, and of course it is dimensionless, which is why we can take the logarithm of the number. Correspondingly, the free energy of the products, or the product in this case, is increased by an amount log C. So, if we therefore write down the actual free energy for the reaction as the free energy difference in standard conditions, which will be negative if the reaction is spontaneous, we have to add to that a term RT log of C, because as the concentration of reactants goes up, the free energy, remember delta G is 0, is reduced for driving the reaction. But as the concentration of the reactants goes up, the free energy is decreased. Writing this all down now in terms of just one logarithm, this ratio then of activities, C over A times B. This quantity here is called the reaction quotient Q, and in the text we discuss how this number is derived for non-simple one-to-one reactions. You will have seen this result, the Nernst equation, many times in chemistry derived from the principle of detailed balance. Here we have obtained this result from the partition function, giving a microscopic picture to the concentration dependence of reaction free energy differences.